Hello everyone, I'm Kayhan. I'm a PhD candidate here at the University of Toronto in the physics department under the supervision of Professor Dick Peltier. And today I'm going to be talking about pushing the limits of global ocean modeling on the Trillium Supercomputer. So I'm going to start with this picture. It's our planet where we all live, seen from space. First of all, it's beautiful. And but more importantly, it reminds us that most of Earth, more than 70% of the Earth is covered by the ocean. And if we think of Earth as a complex system made up of different components, the geosphere, the atmosphere, the ocean, sea ice, land ice, the biosphere, where all these components interact in nonlinear ways, what I'm going to argue in the next few slides is that the ocean is one of the most important components of that system, if not the most important to study and to model. This is another introductory slide that I wanted to include because it helps set the right expectations. It's an article from Quantum Magazine. Part of the reason I included this is because of this cool header image. I mean, if you compare this illustration to the photo of the Earth from space on the previous slide here, it this is this is clearly a cartoon of reality, right? But that is exactly the point of this slide. The header reads, over the past 60 years, scientists have largely succeeded in building a computer model of Earth to see what the future holds. One of the most ambitious projects humankind has ever undertaken has now reached a critical moment. And this is another paragraph from the article that says, for centuries, humans have sought to understand the intricate workings of our planet. As vulnerable creatures, we crave some control over nature, or at least to a handle on coming shifts in the weather and climate. But Earth is a chaotic beast, sensitive to innumerable tiny details. We can't possibly keep track of every speck of dust. The goal of climate modeling is really to build a fake version of Earth, a coarse-grained copy of the planet that's stripped down to the processes that we think are relevant. Now, keeping that Earth system perspective in mind, this slide shows the planet's energy budget. On the left here is a schematic from the 2021 report of the Intergovernmental Panel on Climate Change, which is essentially a synthesis of the scientific literature. And the key message I want to highlight is this. More than 90% of Earth's excess heat is stored in the ocean. And the diagram on the right breaks this down by Earth system components, since the start of the industrial era. And it tells the same story. The blue is the ocean, split into the upper ocean, mid depths, and interior, the deep ocean. And taken together, the ocean has absorbed on the order of 400 zettajoules of anthropogenic excess heat. And to put that in context, one zettajoule is 10 to the 21 joules, roughly equivalent to the energy of about 16 million Hiroshima-sized nuclear explosion. It's an almost unimaginable amount of energy on human scales. And in comparison here, the purple, less than 1% of the excess heat is in the atmosphere. And this is why the ocean acts as a massive heat buffer. We are warming, but if it wasn't for the ocean, that warming would be happening much faster. And the same idea applies to carbon. The ocean is also a major reservoir of carbon and other greenhouse gases. And this buffering role is really one of the main reasons why modeling the ocean accurately is so critical. Another reason the ocean is so important is that because it's fluid, and so because it's fluid, it moves around and it carries properties around, particularly transports heat around the planet. Again, we are warming, but it's not warming uniformly. And the ocean plays a huge role in setting the global pattern and distribution of that heat through its circulation. So if we really want to understand where and how the planet is warming and on what time scale, we really need to understand ocean circulation, and we need accurate models to do that. There are many more reasons why the ocean matters, but I'll stop here, and I hope this is enough to convince you that understanding the ocean, its rich physics, and modeling it accurately is essential. It's not unfair to say most of the climate scenarios are written in the ocean, but are reflected in the atmosphere. Having said all that, studying the ocean is complicated. The ocean contains a whole zoo of strongly coupled physical processes, spanning an enormous range of spatial and temporal scales, from millimeters to the entire globe, and from fraction of a second to thousands of years. The diagram on the right here, this is known as the Stummel diagram, named after Henry Stummel, one of the pioneers of physical oceanography. And what this diagram does is categorize ocean processes by scale. Along the horizontal axis, you have spatial scales from 1 millimeter to 10,000 kilometers. And on the vertical axis, we have the time scale from 10th of a second to 10,000 years. What you can see is that there are many different processes spread across this space, overlapping and interacting with one another. This figure on the left, this gives a more physical picture of some of these processes. Near the surface, there are many processes that control the exchange of properties with the atmosphere. But once those properties are transported into the ocean interior, a whole different set of complex and fascinating processes take over. The good news is that we actually know the physical equations that govern the ocean. You don't need to know the details of these equations, but these come from fundamental uh, physics, conservation of momentum and mass and heat and salinity, together with hydrostatic balance and then equation of state from thermodynamics. Taken together, these are known as the Navier-Stokes equation, and they prescribe how the ocean evolves in time. But of course, we can't really do anything useful with these equations just in our head, because these are far too complex to understand just by staring at them. What we need instead is to solve them numerically, and that's where ocean models come in. So what we do in practice is we take the globe and break it up into many small regions, little rectangles or grid cells. And so we solve those equations for each of these grid cells. There are different ways to this, for this discretization of the globe. And the main variables we carry are properties like temperature and pressure and velocity, and there are different numerical choices as to where those properties live. They can be at the cell center, or they can be at the corners or at the edges, but it doesn't matter. Those are numerical details. The main idea is simple. We discretize the globe and we solve the physics on each grid cell. In our case, we use latitude longitude grid, which wraps around the globe, combined with a special treatment at the North Pole. This is known as the LLC grid, which stands for latitude longitude cap. You can see this in this central image here. Antarctica is land, so we don't need to model ocean there. And in the Arctic, this cap, this is designed so that it corners lie over land, so that this avoids numerical problems, like singularities or distorted grid cells that you'd otherwise get. We do the same thing in the vertical. The ocean is divided into vertical levels, and we then solve the governing equations numerically within each three-dimensional grid cell. Now, this slide shows this gridding scheme of the global model in a bit more detail. As I said, we use the LLC grid, phases 1, 2, 4, and 5. they basically, that they form the latitude-longitude wrap around the globe. And phase 3 is the polar cap. Geometrically, that's fairly straightforward, but numerically, things get more complicated because on a computer, we work with linear arrays and binary files. So the figure on the left here shows how this grid is actually laid out in memory and is stored on disk. Now, this introduces some non-trivial complexities. For example, if you want to trace the zonal velocity around the equator, it's stored as the u variable in some phases, but then in some other phases, it's stored as the v variable, depending on where in the globe we are. But more generally, whenever we want to visualize the global field or interpolate a solution from a low resolution model to a high resolution, we have to apply a series of rotations, shifts, and transformations, especially for vector fields like velocity, because they are intertwined. And these are not small data sets. Each file can be hundreds of gigabytes. So all of this has to be done in highly parallel optimized way. And we have developed all the infrastructure for data manipulation, visualization, and regrading on Trillium. We have that infrastructure now. Okay. Now, to say a few words about the size of the models we are running, you may have seen names like LLC 1080, LLC 4320, LLC 8640 in the abstract of my talk. I've already explained where the term LLC comes from. The number in front simply refers to the horizontal grid resolution. So, for example, if the number is n is the grid cell count across the width of a single face in the LLC grid. So here is n, here is n, this is n, this is n, and this is n. For faces 1, 2, 4, and 5, the grid is n cells wide and 3n cells long, which gives 3n squared grid cells per face per vertical level. Phase 3 is the polar cap. It's just n by n. And if you add everything together, the full grid contains 13n squared grid cells per vertical level. And once you multiply that by 173 vertical levels that we have, you quickly end up with models that are extremely large. Now, to put some rough numbers on this, for LLC 1080, if you take 13 times 1080 squared and multiply by 173 vertical levels, you end up with on the order of 10 to the 9 grid cells. This is what we consider our baby model. Even so, running it requires at least 13 nodes on Trillium and a single snapshot of one 3D field. That has a size of on the order of about 10 gigabytes. Now, LLC 4320, this is, I would say, the current state-of-the-art model in the community. This has on the order of 10 to the 10 grid cells. One snapshot of a single 3D field is around 150 gigabytes. And to run it on Trillium, we need essentially the maximum allowed node allocation per job, 110 nodes, just to integrate the model forward at roughly one simulated day per wall clock day. With fewer nodes, we simply run out of memory. We can't start the simulation. And finally, the highest resolution model that we're aiming to run, LLC 8640, has on the order of 10 to the 11 grid cells. A single snapshot of a three-dimensional field is already more than 600 gigabytes. And at this point, the challenge is not just computation, although that's the main challenge, but it's also data handling. Even holding a single time slice of one variable in memory becomes difficult, which has major implications for data manipulation and visualization. And we are happy to have developed all the necessary infrastructure on Trillium. Now, during the beta testing phase of Trillium, we tested this configuration and found that we can run it using roughly half of the machine, around on the order of 600 nodes. But with further optimizations, like removing the blank tiles, we may be able to reduce that to a third of the machine or a fourth of the machine, but that work is still ongoing. We are not sure about the exact number yet. Okay. So what you're looking at here is a real global ocean model, the classic LLC 4320. This was originally run at JPL about 20 years ago. But even today, this remains one of the state-of-the-art global ocean models. It's run on the Trillium Supercomputer at NASA, and the lead scientist behind the development of this model, Dimitri Menemelis, is with us today and is helping us develop the next generation of these models. You know, he grew up in Montreal, and we are very fortunate to have him involved. This animation shows the global ocean circulation. And what you're seeing here is the sea surface speed, but of course the model itself is fully three-dimensional. And you can already recognize many familiar features like Kuroshio, for example, or this is the Gulf Stream here. Or there are some strong tidal currents. Now I let the animation progresses. This is where what we call the tropical instability waves should exist. This is here is Antarctica, and this current you see around it, this is Antarctic circumpolar current, ACC. It's a powerful ocean current that flows all the way around Antarctica because of some strong winds. And I say this because I'll revisit ACC in some of the later slides. Now, okay. So if you zoom in, you start to see much more detail, you know, ocean eddies, strong currents, internal tides, and many other features. And one of the unique aspects of this simulation is that it saves the full three-dimensional ocean state every hour, everywhere. And the idea is that, okay, this model is not the real ocean, it's an imperfect representation. But in the real world, our observations are extremely sparse. You know, you could go to the real ocean, drop a mooring, or do a CTD cast, or run a ship transect. We can only see tiny pieces of the ocean in space and time. And this simulation lets us ask a different question. What could we learn if we had complete continuous observations of the ocean physics? You know, as much as captured by the model at every location, at every moment in time. Even though it's not truth, it has some degree of realisms. And that makes it incredibly powerful as a reference data set. Another key feature of this simulation is that it includes both atmospheric forcing in the surface and tides, you know, external and internal tides. And these high resolution, quote unquote, wind plus tide models don't just reproduce larger scale circulation. They do that, but they also admit part of the internal wave continuum. That makes them especially interesting for studying wave spectra and wave breaking and turbulence, which are central to my own research. So this was a major motivation for running the model. It was also done in preparation for the SWOT mission to better understand what such a mission might observe, which I'll explain in some of my future slides. Okay. So to talk about some of the research we did using Niagara before the Trillium era, and using this LLC 4320 model, I need to introduce a little bit of ocean physics. The next few slides get a bit more dry and physics heavy, so please bear with me. I just want to share some of what we learned from LLC 4320 before moving on to the main topic of the talk. So on the left here is a schematic of the global overturning circulation. And the horizontal axis runs from Antarctica all the way in the south, right? All the way to the North Pole. And the y-axis is depth. What this schematic shows is that water here, if you look at here and here, water sinks into the deep ocean at high latitudes, both around Antarctica and in the North Atlantic. Now, here is the key point. If the ocean is in a steady state, all of the water, I'm talking on this schematic on the right here now. If the ocean is in the steady state, all of the water that sinks in the two poles, um, all of the water that sinks to the abyss eventually have to come back up somewhere else. And the idea goes back to Walter Munk, one of the founders of modern oceanography. Munk basically argued that because the total volume of the ocean water is not changing, the sinking dense water at high latitudes must be balanced by a slow, widespread upwelling throughout the ocean interior. Without going into the details of his calculation, he estimated that this vertical velocity is on the order of 3 meters per year. That's an extremely weak flow, especially compared to horizontal ocean currents, but it must exist in order to close the ocean's mass budget. Now, building on that, Monk made a clever observation. This diagram here on the right, this shows observations of temperature in the Pacific Ocean. You can see that the temperature decreases from about 4 degrees in 1 kilometer depth to about 1 degrees in 5 kilometer depth. And Monk argued that if cold water is slowly moving upward from the abyss, then this upward transport must be balanced by a downward transport of heat from the above. Otherwise the system couldn't be in thermal balance. And the simplest way to represent that balance is with an advection diffusion equations. Again, you don't need to know the details, but basically here on the left-hand side, we have an advection term. It's a vertical advection. And on the right-hand side, we have a diffusion of heat from the ocean surface down to the ocean interior. And then using this balance, Monk estimated an effective vertical diffusivity of about 1 centimeter squared per second. Now, this value has become a canonical number in physical oceanography. Now, here's the key issue. The Monk's canonical value of 1 centimeter squared per second, that's roughly 3 orders of magnitude larger than the molecular diffusion coefficient of seawater. So molecular diffusion alone cannot be responsible for transporting heat from the surface down into the ocean interior. So the process doing this must be much more efficient, something like turbulent mixing. A useful analogy is coffee. You don't wait for sugar to diffuse molecularly in your mug, right? In your coffee. You stir it. And the question is, in the ocean, what are the effective spoons that steer heat downward? And most large-scale ocean motions that we know, they move along density surfaces, not across them. For some physical reasons, stratification and rotation constrain the flow, which means larger scale currents are actually very inefficient at mixing heat vertically. And now for decades, it's been hypothesized that small scale processes, and in particular, the breaking of internal gravity waves are responsible for this enhanced mixing. Internal waves exist at the interfaces between layers of different density. If you look at here, for example, imagine this is a layer of warm water on top of a layer of colder water, right? And internal gravity wave exists at the interface, just like just like the surface waves at the air-sea interface. The physics is essentially the same. When these waves are too large, they can overturn and break and mix. So it's hypothesized that these are the efficient spoons that are mixing, that are steering heat downward from the ocean surface down to the ocean interior. Now, the challenge is that the ocean interior is a very quiet place. At any given location, you might see on average 1 breaking event per day. And these events are very intermittent in both space and time. So that makes them extremely difficult to observe directly. And this is why, these high resolution numerical ocean models are so powerful. They give us a continuous four-dimensional view of the system everywhere, all the time. And this is my last dry physics heavy slide, I promise. And then I move on to the main topic. Even at its very high resolution, LLC 4320 is still not enough to fully resolve internal wave breaking. So what we did instead was we extracted the regional box in the Pacific and dynamically downscaled it by a factor of 8 to much higher resolution. And these simulations were all run on Niagara. Using these regional simulations, we were able to show two key results that I'm personally very proud of. First, when the resolution is sufficiently high, internal wave breaking alone can produce the canonical Monk value of about 1 centimeter squared per second, even though those breaking events are rare and highly intermittent. We showed that, internal wave breaking alone can produce that amount of diffusivity. And second, if you look at here, we directly identify the mechanism of this breaking, the mechanism by which this mixing occurs. This figure, instead of looking at waves in physical space and time, we are looking at how kinetic energy is redistributed across internal wave normal modes. Each of these lines in this space is an internal wave mode. Blue is negative, red is positive. So when we allow internal wave breaking to happen in the model, we see that energy is drained from the order modes and is deposited into higher order modes. And these higher order modes correspond to smaller spatial scales. And these higher order modes have very strong vertical shear in their horizontal velocity, which makes them susceptible to what we call shear instability and ultimately to breaking and mixing. So the main story that I want to say here is that although it's long been hypothesized that breaking internal waves are responsible for the Monk value of turbulent diffusivity, this is the very first time that we demonstrate the full mechanistic pathway directly using numerical simulations. And this has only been made possible by the generous support of the Digital Research Alliance of Canada. Okay, I'm moving to the main topic of the talk now. Now, as of 3 years ago, a NASA mission that some of you may have heard of, the Surface Water and Ocean Topography, SWOT mission, was launched. And at its core, SWOT is a satellite altimeter that measures sea surface height, but it does so with unprecedented accuracy. I'm not an expert on the instrument and the data set. I'm still learning this. But the basic idea is this. If you look at here, the bluey dots that you see here, these are observations from previous generations of altimeters. And in contrast, this is SWOT. It provides measurements that are about an order of magnitude more precise. And when you zoom in here, the level of detail is remarkable. For the first time, we can directly observe surface signatures of internal waves from space. Now, this is an actual SWOT data. For the first time, we can begin making direct, meaningful, comparisons between high-resolution ocean models and satellite observations at these scales. And these comparisons are being carried out by us as well as our collaborators at the University of Michigan and Woods Hole Oceanographic Institution using the same regional simulations that I mentioned earlier that were run on Niagara. That body of work, those numerical simulations, has led to a number of publications of, all of which acknowledge Compute Canada and then the Digital Research Alliance of Canada for their support. What's shown here is internal wave spectrum in the wave number space. The blue curve here is abyssal, which is basically our previous observational understanding of sea surface height variability. The red curve is LLC 4320, and the black is SWOT. And you can see at larger scales, LLC 4320 captures a substantial fraction of the internal wave spectrum. But as we move to smaller scales, it clearly falls short compared to what SWOT is now observing. Now, even when we increase resolution by a factor of 8 in regional simulations, you see this pink curve here, we still miss some of the finest scale variability seen by SWOT. And this mismatch has created a real sense of urgency in the community to build next generation global ocean models that can operate at these scales. And that's exactly where we are now. With the availability of Trillium, we are in a position to push global ocean modeling into this new observational regime. Now, this is once again the STOML diagram. And on this diagram, red corresponds to the global LLC 4320, and blue shows the LLC 8640 simulation that we are planning to run. LLC 8640 will have a shorter duration, but a higher spatial resolution. And when I say that we are quote unquote pushing the limits of global ocean modeling here, this is exactly what I'm referring to, this narrow region here. We're trying to move global simulations into this region of the diagram. And we can better resolve and understand internal waves and internal tides and some finer scale motions. Now, beyond resolution, there are several well-known issues with LLC 4320 that have been identified over the past 20 years. I'll very briefly highlight a few of them and then explain how we are addressing these long-standing problems in the next generation of global ocean models. The first issue has to do with the Gulf Stream path. The Gulf Stream is a powerful warm current that transports heat from Gulf of Mexico across the Atlantic, and it plays a major role in keeping Western Europe much warmer than it would otherwise be. However, virtually every single study shows that in LLC 4320, the Gulf Stream is displaced too far south compared to observations. In fact, these two figures come from presentation titled "The Gulf Stream, Yikes, What It's Doing Down There." And it's a humorous title, but it captures a persistent bias in the model. Turns out this was caused by the poor bathymetry used in the model that we have resolved now. A second issue that has been repeatedly reported in LLC 4320 concerns tropical instability wave here. So tropical instability wave, it's a slow wave-like wobble of warm water near the equator that plays an important role in mixing warm and cold water in the tropical Pacific. In LLC 4320, these waves are essentially absent or very weak. And the most likely reason is that the equatorial undercurrent in the Pacific is too weak, which I'll talk about later. And this is something we are actively working on to fix in the new model configuration. And the third well-documented issue involves the Antarctic circumpolar current, which I briefly mentioned earlier. In LLC 4320, the representation of the ACC is quite crude, and this is likely because the model did not include ice shelf cavities, particularly around Antarctica, but also around Greenland. And these ice-ocean interactions are essential for getting the Southern Ocean dynamics right. And these are very broad, long-standing issues, each involving distinct physics and dynamics, and each could easily be the subject of a separate talk on its own. And I'm not necessarily an expert on them, but fortunately we're working with an excellent team of physical oceanographers across multiple institutions who are helping us identify, diagnose, and fix these problems in the next generation of global ocean models. Finally, let me turn to what we have developed so far. So building on the classic LLC 4320, we've made a number of key changes to address those long-standing issues. First, of course, we have increased the resolution. Second, we are using an updated bathymetry with much finer representation of seafloor structure now. We now use a nonlinear free surface, which essentially gives a more accurate pressure solution, especially in shallow regions and the long coastlines. We've added ice shelf cavities, both around Antarctica and Greenland, which are essential for realistic Southern Ocean polar dynamics. We're forcing the model with hourly atmospheric fields, rather than the 6-hourly forcing used in the classic configuration. And finally, we're using more accurate tidal forcing than what was available during the original LLC 4320. And together, these changes represent a substantial step forward in the realism of global ocean modeling. Now, to show you the new model in action, this is the new or refined LLC 1080, our baby model. This one is run on Trillium. So what you're seeing here is an animation of sea surface speed. Beige is land, white is sea ice, steel blue is shelf ice, and the colors are sea surface current speed based on this color bar above here. So this model starts from rest, and as it integrates forward, it spins off and gains kinetic energy. You can see the evolution of both kinetic energy and potential energy, but pay a particular attention to the kinetic energy on this plot here. This shows how kinetic energy first oscillates, that's due to the tides, but also there is an upward trend when we integrate in nearly a year-long duration of the integration. So this shows that the model is spinning up and is gaining kinetic energy. And this animation is also generated on Trillium. At places like NASA Ames, there are dedicated visualization teams that produce the classic LLC 4320 animation I showed you earlier. We don't have that level of visualization support yet. So apologies for aesthetic, but the physics is all here. And in terms of dynamics, within hours after we start running the model from rest, within hours we see barotropic adjustments and tides emerge. Over days to weeks, interactions between barotropic motions, stratification, and topography generates internal tides, and geostrophic adjustments sharpens currents and boundary jets. Over weeks to months, these currents become baroclinically unstable, and they fill the domain with mesoscale eddies and fronts. And overall, it takes about a year, maybe a year and a half, around 14 months, to reach a quasi-equilibrium in terms of the kinetic energy of the system. Again, if you look at this plot here, it takes about a year, somewhere between a year and a year and a half, to reach a stage that the kinetic energy only oscillates. There is no upward trend anymore. And that's what we call a quasi-equilibrium. The system is spun up enough. And our plan is to, use this spun up LLC 1080 state as initial conditions of a new LLC 4320, to jump the resolution after the spin up is finished, to run that LLC 4320 for about 6 months. And then from there, we'll jump once again in resolution to LLC 8640 and integrate for roughly a month at that unprecedented global resolution. Okay, so to show you some of the improvements in the new model, this figure shows the Gulf Stream path. The top and the middle panels, they're basically for LLC 10, the classic LLC 1080, and the bottom panel shows the new LLC 1080 configuration. As you can see, in the new model, the Gulf Stream has shifted northward, where it should be. So that's what we already see in our baby model. Here's another example of the improvements we're actively working on. The equatorial undercurrent is a persistent eastward flowing jet that is below the surface along the equator. Now, these plots show eastward velocity with time on the horizontal axis and depth on the vertical axis. The two middle panels here, they are observations and they are identical. And as you can clearly see, there is a strong persistent eastward current around 150 meters depth. And the two panels at the top are model results using two different parameter settings. And these parameters mainly affect the turbulent and mixing in the model that I talked about earlier. In the configuration that was closest to the classic LLC model here on the left, the undercurrent is much too weak, right? But in contrast, this is for one of our newest configurations. This one, we can see that there is a much stronger and more realistic undercurrent. In fact, we have run multiple of such sensitivity experiments and with our baby model. And in this summary plot here, we're basically showing, you see the yellow curve is where we started from. The blue curve is the observation, and the magenta is one of our most recent simulations. So you can see the progress we've made so far. We are planning to run a few of other such sensitivity experiments. And then the final step will be to ask the question, what linear combination of these parameters best minimizes the mismatch between the model and the observation? And that it's a tuning task, it's an optimization. And that optimized set of parameters, whatever that will be, that will be used in the next generation LLC 4320 and LLC 8640 simulations. Okay. I've talked a lot about the models and the improvements we're making, but it's important to be clear about where we are right now. With the exception of the LLC 1080 spin-up, we don't yet have the resource allocation needed to run the high resolution models this year. The tables you see here come from our resource allocation proposal for next year. To execute the full plan, we're requesting on the order of 21,000 core years of computing time, and along with a little over 7 petabytes of storage. We've also been working with SciNet to enable us to run single jobs on a significant fraction of the machine, more than 110 nodes. It's been extremely encouraging to see strong support from the SciNet team. And if this allocation request is granted, we're ready to move immediately and start building global ocean models that will become important data sets at the international scale and help establish Toronto as a leading center for global ocean modeling. In conclusion, global ocean modeling is essential for understanding the climate system as well as the geophysical fluid dynamics and complex physical processes occurring in the oceans. LLC 4320 was an impactful global ocean simulation conducted by JPL NASA, which we used on the Niagara supercomputer to investigate the physics of wave breaking and diapicnal diffusivity. There were several well-known issues with LLC 4320, including a misplaced Gulf Stream, anemic tropical instability waves, and the crude representation of Antarctic shelf currents. There is also a growing urgency to develop even higher resolution global ocean models, especially given that LLC 4320 is nearly 20 years old and in light of the launch of SWOT. We have refined the global LLC model and have introduced new physics to address its long-standing issues. During the beta testing phase of Trillium, we conducted a short test run of LLC 8640 on Trillium and are confident that Trillium can handle the computations. We are currently optimizing model parameters by comparing the global model against observations and they're spinning up the low-resolution LLC 1080. And if our next year's resource allocation request is granted, we are prepared to immediately begin building the refined LLC 4320 and progress towards LLC 8640, which is expected to attract significant attention from the international scientific community. Thank you very much for your attention. I'm happy to take any questions.